Tonight, we're going to explore something that shouldn't exist. A world hiding in the darkness beyond Neptune. Not Planet 9 that scientists have been searching for in the far outer solar system, but something different. Something closer. Something stranger. A small, rocky planet that might be warping the outer edge of our solar system right now. And by the end of tonight, you're going to understand what led astronomers to this discovery, and what it means for everything we thought we knew about our cosmic neighborhood. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now, let's begin. Here's what you think you know about our solar system. You learned in school that there are 8 planets: Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, and Neptune. 8 worlds circling the Sun in neat, predictable orbits. The inner 4 are small and rocky. The outer 4 are massive gas and ice giants. Beyond Neptune, there's the Kuiper Belt, a region of icy debris left over from the solar system's formation. And that's it. That's the complete picture, or so we thought. But here's the thing most people don't realize. The outer solar system is vast, dark, and mostly unexplored. Neptune orbits at about 30 times Earth's distance from the Sun. Light from our star takes over 4 hours to reach Neptune's orbit. Beyond that, in the Kuiper Belt and beyond, there are regions so dark, so distant, that we've barely scratched the surface of what's out there. We've discovered thousands of small icy bodies in the Kuiper Belt. But these objects are tiny, measuring tens or hundreds of miles across. They're incredibly difficult to spot because they're so far away and reflect so little sunlight. It's like trying to find a charcoal briquette floating in the middle of the Pacific Ocean at midnight. From orbit, around the moon. That's the challenge astronomers face when searching for distant objects in our solar system. And yet, despite these challenges, they keep finding things that don't quite fit. Patterns that suggest something bigger is out there. Something we haven't found yet. Let me take you back to the beginning of this story. In late 2025, a team of astronomers published a paper that sent ripples through the astronomical community. They weren't claiming to have found a new planet. They were claiming to have found evidence that one exists. The evidence came from something unexpected: a warp, a tilt in the outer Kuiper Belt that shouldn't be there. Think of the Kuiper Belt as a cosmic disk of icy debris. It starts roughly where Neptune's orbit ends and extends outward for billions of miles. The objects in this belt should all be orbiting in roughly the same plane, like marbles rolling around the rim of a shallow bowl. This makes sense because the entire solar system formed from a spinning disk of gas and dust around the young sun. Everything should still reflect that original flatness. And for the most part, it does. The 8 major planets all orbit in nearly the same plane. The inner Kuiper Belt objects do the same. But when astronomers looked at the outer Kuiper Belt, the region beyond about 48 astronomical units from the Sun, they found something strange. An astronomical unit is the distance from Earth to the Sun, about 93 million miles. 48 astronomical units is 48 times that distance. About 4,464,000,000 miles. That's nearly twice as far as Neptune. In this distant region, the Kuiper Belt isn't flat anymore. It's warped, tilted, twisted out of the plane where it should be. The objects out there are orbiting at an angle, as if something has pulled them off their original paths. Now, you might think this could be random. Maybe these objects just happened to form with tilted orbits. Maybe they got knocked around by collisions or gravitational interactions long ago. But the tilt isn't random. It's consistent. The outer Kuiper belt objects are tilted in the same direction by roughly the same amount. That's not chance. That's a pattern. And patterns in astronomy usually mean something is causing them. Something with gravity. The astronomers who discovered this pattern did what scientists always do. They ran computer simulations. They created virtual solar systems and tried different scenarios to see what could produce this warp. They tried collisions between large objects, gravitational interactions with Neptune, the influence of passing stars billions of years ago. Nothing they tried could reproduce the observed warp, except one thing: adding another planet. When they placed a small rocky planet in the outer solar system at a specific distance and with a specific orbit, suddenly the warp appeared in their simulations. The planet's gravity would slowly tug on the Kuiper belt objects, pulling them into tilted orbits over millions of years. The simulation matched the observations. That's how science works. You observe something unexpected. You try to explain it with known phenomena. When that fails, you consider new possibilities. And sometimes, those possibilities are planets we didn't know existed. They called this hypothetical world Planet Y. Not because it's the 25th planet. Planet Y is simply a designation, a placeholder name, until and unless the planet is actually found and officially named. So what exactly is Planet Y supposed to be? Let's talk about the details, because they matter. Planet Y isn't another gas giant, like Jupiter or Saturn. It's not an ice giant, like Uranus or Neptune. Based on the simulations, Planet Y would be a small rocky world, somewhere between the size of Mercury and Earth. Mercury, the smallest planet in our solar system, measures about 3,030 miles across. Earth measures about 7,918 miles across. So Planet Y would fall somewhere in that range. A terrestrial planet like the worlds of the inner solar system, but lost in the darkness of the outer solar system. That's unusual. The rocky planets in our solar system are all close to the Sun. The giant planets are farther out. This arrangement makes sense based on how the solar system formed. Close to the young Sun, it was too hot for ice to exist. Only rock and metal could condense from the swirling disk of material. That's why the inner planets are small and rocky. Farther out, beyond what's called the ice line, ice could condense along with rock and metal. This gave the outer planets much more material to work with. They grew massive, their gravity pulling in huge amounts of hydrogen and helium gas from the surrounding nebula. That's why the outer planets are giant balls of gas and ice. But Planet Y doesn't fit this pattern. If it exists, it's a rocky world in the outer solar system, a world that formed close to the Sun and somehow ended up billions of miles away. How could that happen? There are a few possibilities. One idea is that Planet Y formed in the inner solar system along with Mercury, Venus, Earth, and Mars. During the early chaotic days of the solar system, gravitational interactions were wild. Planets were still finding their final orbits. The giant planets, Jupiter and Saturn especially, were moving around, their massive gravity fields disrupting everything nearby. It's possible that one of these interactions flung a small rocky planet outward. Think of it like a gravitational slingshot. The planet swings close to Jupiter or Saturn. The giant planet's gravity accelerates the smaller planet, throwing it into a much larger orbit. This isn't just speculation. We know gravitational interactions like this happened. Computer models of the early solar system show that the giant planets didn't form where they are now. They migrated inward and outward over millions of years. Jupiter probably formed farther from the Sun and moved inward. Saturn, Uranus, and Neptune all moved outward. This migration would have scattered countless smaller objects. Some fell into the Sun. Some were ejected from the solar system entirely. Some were thrown into distant orbits. Planet Y could be one of those scattered worlds. A rocky planet that formed close to the Sun but was kicked out to the edges of the solar system by a close encounter with a giant planet billions of years ago. Another possibility is that Planet Y formed where it is. This seems unlikely, given what we know about planet formation, but it's not impossible. If there was a local concentration of rocky material in the outer solar system, perhaps left over from some earlier process, a rocky planet could have formed there. We don't know enough about the fine details of our solar system's formation to rule this out completely. There's also a third, more exotic possibility. Planet Y could be a captured rogue planet. A world that formed around another star, was ejected from its home system, and wandered through interstellar space until our Sun's gravity captured it. This sounds like science fiction, but rogue planets are real. Astronomers have detected them drifting through space between the stars. They're difficult to spot because they don't orbit stars, so they don't reflect any starlight. But they do emit faint infrared radiation from leftover heat from their formation. Sensitive infrared telescopes can detect them. We don't know how common rogue planets are, but some estimates suggest there could be billions of them wandering the galaxy. If our solar system captured one billions of years ago, it could still be orbiting out there in the darkness. The simulations that suggest Planet Y exists also tell us where it should be. This is crucial because it determines whether we can find it. According to the models, Planet Y would orbit somewhere between 40 and 70 astronomical units from the Sun. But let me be more specific about what the simulations actually show. The astronomers who published this research didn't just run one simulation, they ran thousands. Each simulation started with a slightly different configuration. Different masses for Planet Y. Different orbital distances. Different orbital inclinations. Different eccentricities. They wanted to explore the full range of possibilities. For each simulation, they let the virtual solar system evolve forward in time for billions of years. They tracked how the Kuiper Belt objects moved under the influence of the giant planets and the hypothetical Planet Y. Then they compared the final configuration to what we actually observe. Most configurations didn't work. Either the Kuiper Belt remained flat, or it developed a warp in the wrong direction, or the warp was too large or too small. Only a narrow range of parameters produced a warp that matched observations. Those successful simulations all had Planet Y in roughly the same location, between 40 and 70 astronomical units, with a mass between half Earth's mass and 1.5 times Earth's mass, on an orbit tilted maybe 10 to 30 degrees relative to the main plane of the solar system. These aren't exact numbers, they're ranges, but they narrow down where to search. The simulations also revealed something interesting about timing. The warp we see today took time to develop. Planet Y's gravity doesn't instantly tilt all the Kuiper Belt objects. Instead, over millions of years, the planet's repeated gravitational tugs slowly change their orbits. Some objects get tilted more than others. The effect accumulates over time. In the simulations, it took roughly 100 million to 500 million years for the warp to become as pronounced as what we observe. This timing is important. It tells us that if planet Y exists, it's been in its current orbit for at least that long, probably much longer. If planet Y was recently scattered into the outer solar system, maybe only 10 million years ago, there wouldn't have been enough time for the warp to develop. The Kuiper belt would still be relatively flat. But if planet Y has been out there for hundreds of millions or billions of years, that's plenty of time. So the simulations don't just tell us where planet Y is. They tell us it's been there for a long time. It's not a recent visitor. It's an ancient resident of the outer solar system. Another detail from the simulations involves the specific Kuiper belt objects affected by the warp. Not all Kuiper belt objects are warped. Only the ones in a particular distance range. Objects closer than about 48 astronomical units are mostly unaffected. They orbit in the main plane of the solar system. Objects between roughly 48 and 60 astronomical units show the strongest tilt. Objects beyond 70 astronomical units are more scattered and harder to characterize, but they don't show the same coherent warp. This pattern makes sense if planet Y orbits in the mid-Kuiper belt region. Objects close to planet Y would be most strongly affected by its gravity. Objects far from planet Y would be less affected. It's like dropping a stone in a pond. The ripples are strongest near where the stone landed. They fade as you move away. The warp in the Kuiper belt is like a gravitational ripple. Strongest where planet Y's influence is greatest. Weaker, farther away. The simulations predicted this pattern before observations confirmed it. That's a good sign. It means the planet hypothesis explains not just one observation, but multiple related observations. The strength of the warp. The distance range where it appears. The coherent direction of the tilt. All of these match what you'd expect if a small planet was perturbing the Kuiper belt. Of course, simulations are only as good as their assumptions. If the astronomers got something wrong about the masses or orbits of known planets, that could affect the results. If there's some other gravitational influence they didn't account for, that could change things. Science is always provisional. Models are always approximations. But the fact that the planet hypothesis fits the observations so well is compelling. It doesn't prove planet Y exists, but it makes the idea plausible enough to warrant a serious search. Let me put that in perspective. Neptune orbits at about 30 astronomical units. Pluto's orbit is highly elliptical, ranging from about 30 to 49 astronomical units. So planet Y would be beyond Pluto's orbit, in the outer reaches of the Kuiper belt. 40 astronomical units is 3,720,000,000 miles from the Sun. 70 astronomical units is 6,510,000,000 miles. At that distance, the Sun would look like a bright star, not the blazing disk we see from Earth. Sunlight would be incredibly faint. At 40 astronomical units, sunlight is 1,600 times dimmer than it is at Earth. At 70 astronomical units, it's 4,900 times dimmer. That's why finding planet Y is so difficult. It's far away, and it's receiving almost no sunlight to reflect. Even if it's the size of Earth, it would be incredibly dim. The simulations also suggest planet Y would have an inclined orbit. not orbiting in the same plane as the major planets, but tilted at an angle. This makes sense. If planet Y was scattered outward by a gravitational encounter, its orbit would likely be eccentric and inclined. If it's a captured rogue planet, its orbit would definitely be unusual. An inclined orbit makes the search even harder because astronomers have to survey a larger area of sky. Most planet searches focus on the ecliptic, the plane where the major planets orbit. But if planet Y is orbiting above or below that plane, it could be anywhere. That vastly increases the search area. It's the difference between searching a single shelf in a library and searching the entire building. Now, you might be wondering about Planet 9. You might have heard about that in the news over the last several years. Planet 9 is a different hypothesis. It's important to understand the distinction. In 2016, astronomers Konstantin Batygin and Mike Brown published a paper suggesting that a large planet might exist in the far outer solar system. They based this on the orbits of several distant Kuiper Belt objects called extreme trans-Neptunian objects. These objects have very strange orbits. They're all aligned in the same direction, which seems unlikely to be random. Batygin and Brown suggested that a planet roughly 10 times Earth's mass could be shepherding these objects into their aligned orbits. They called this hypothetical world Planet 9. If Planet 9 exists, it would be a super-Earth or mini-Neptune orbiting somewhere between 200 and 1,200 astronomical units from the Sun. That's vastly farther than Planet Y. 200 astronomical units is 18 billion, 600 million miles. 1,200 astronomical units is 111 billion, 600 million miles. That's approaching the inner edge of the Oort cloud, the spherical shell of icy objects that surrounds the solar system at extreme distances. Planet 9, if it exists, would be massive, distant, and incredibly difficult to find. It would receive almost no sunlight. It would take tens of thousands of years to complete one orbit around the Sun. Planet Y is completely different. It's closer, smaller, and based on different evidence. Planet Y would orbit between 40 and 70 astronomical units. Planet 9 would orbit between 200 and 1,200 astronomical units. Planet Y would be the size of Mercury to Earth. Planet 9 would be 5 to 10 times Earth's mass. Planet Y is suggested by a warp in the Kuiper Belt. Planet 9 is suggested by aligned orbits of extreme distant objects. They're two separate hypotheses addressing two different mysteries. It's possible both exist. It's possible neither exists. It's possible one exists and not the other. We won't know until we find them, or definitively rule them out. The search for both planets is ongoing, using different techniques and different areas of the sky. But finding a planet in the outer solar system is extraordinarily difficult. Let me explain why in detail, because understanding the challenge helps you appreciate the achievement when and if Planet Y is found. The fundamental problem is light. Planets don't produce their own light. They shine by reflecting sunlight. The amount of sunlight a planet reflects depends on two main factors: its size and its distance from the Sun. A larger planet has more surface area to reflect light. A planet closer to the Sun receives more intense sunlight to reflect. Planet Y fails on both counts. It's small, probably somewhere between Mercury and Earth in size. and it's far from the Sun, at least 40 astronomical units away. At that distance, sunlight is already faint. At 40 astronomical units, sunlight is 1,600 times dimmer than it is at Earth's orbit. A planet at that distance receives 1,600 times less light to reflect. So, even if planet Y has the same reflectivity as Earth, same size as Earth, and same ability to reflect light, it would appear 1,600 times fainter than Earth would at our distance. But Earth is already invisible to the naked eye from interplanetary distances. You'd need a telescope to see Earth from Mars, and Mars is relatively close. From 40 astronomical units, Earth would require a powerful telescope to detect. Planet Y might be smaller than Earth. That makes it even fainter. Planet Y might have a darker surface than Earth. Rock and ice in the outer solar system tend to be covered with dark organic compounds called tholins. These form when cosmic rays and ultraviolet light interact with simple molecules like methane. Tholins are dark, reddish-brown, similar to the color of Pluto's surface. If Planet Y's surface is covered in tholins, it would reflect less light than a brighter surface would. That makes it fainter still. When you combine the small size, the great distance, and the possibly dark surface, Planet Y would be incredibly faint. We're talking about an object with a visual magnitude of perhaps 23 to 26. Magnitude is how astronomers measure brightness. Lower numbers are brighter. The Sun has a magnitude of -27. The full moon has a magnitude of -13. The brightest star in the sky, Sirius, has a magnitude of -1.46. The faintest stars visible to the naked eye, under perfect dark sky, conditions have a magnitude of about 6. Pluto, at its brightest, has a magnitude of about 14. You need a decent amateur telescope to see Pluto, Planet Y, with a magnitude between 23 and 26, would be hundreds or thousands of times fainter than Pluto. You'd need one of the largest telescopes on Earth to detect it. And even then, it would be right at the limit of detectability. Every observation would be pushing the telescope to its limits. Background noise from the detector, light pollution, atmospheric turbulence, all of these factors make it harder to detect faint objects. Planet Y would be barely above the noise level. Easy to miss. Easy to confuse with instrumental artifacts or background galaxies. This is where the challenge becomes not just about sensitivity, but about patience and systematic searching. Astronomers can't just point a telescope at the sky and immediately spot Planet Y. They need to take multiple images of the same region of sky over time. Then they need to compare the images to look for objects that moved. This technique is called time domain astronomy. It's how most asteroids and comets are discovered. It's how Clyde Tombaugh discovered Pluto in 1930. He photographed regions of sky on different nights. Then he used a device called a blink comparator to rapidly switch between images. Stationary objects like stars would appear in the same place in both images. But moving objects, like planets or asteroids, would shift position. By blinking back and forth between the images, the moving object would appear to jump. That's how Tombaugh spotted Pluto. A faint dot that moved slightly between photographs taken 6 days apart. Modern searches use the same principle, but with digital cameras and computers. Telescopes take images of patches of sky. Software analyzes the images, identifies all the objects, and measures their positions. Then, the software compares images taken on different nights. Any object that moved is flagged as a potential solar system object. The problem is that there are a lot of moving objects in the solar system. Thousands of asteroids, hundreds of Kuiper Belt objects, spacecraft, satellites. Most of these are already known. The software has to check each detection against a database of known objects. If an object matches a known asteroid or Kuiper Belt object, it's discarded. What remains are the unknowns. New detections. But even these are mostly false positives. Cosmic rays hitting the detector can create bright spots that look like stars. Artifacts from image processing can create spurious detections. Distant galaxies can sometimes be mistaken for moving objects if the images aren't aligned perfectly. Astronomers have to carefully vet each candidate. They take follow-up images to confirm the motion. They calculate a preliminary orbit to see if it makes sense. They check the brightness to see if it's consistent with a solar system object. This process is time-consuming. A single night of observation might produce hundreds or thousands of candidate detections. Most will turn out to be noise or known objects. A few will be real new discoveries. But the vast majority of those discoveries will be small asteroids or Kuiper Belt objects, not Planet Y. Finding Planet Y is like finding a needle in a haystack. Except the needle is invisible unless you shine a light on it. And the haystack is the size of the sky. And there are thousands of other needles mixed in. And you can only search a tiny portion of the haystack each night. That's the magnitude of the challenge. It requires systematic surveys covering large areas of sky. It requires sensitive detectors capable of detecting faint objects. It requires sophisticated software to process the data and identify candidates. It requires follow-up observations to confirm detections. And it requires patience. Years or decades of patient searching. When we search for planets around other stars, we use techniques that don't work for our own solar system. We can look for the tiny dimming of a star's light as a planet passes in front of it. That's called the transit method. We can look for the wobble in a star's motion caused by a planet's gravity pulling on it. That's called the radial velocity method. But these techniques require a bright star. They don't help us find planets orbiting our own sun from our perspective. Instead, we have to find planets in the outer solar system by direct observation. We have to actually see them in telescopes. And that's incredibly challenging. A planet reflects sunlight. The amount of light it reflects depends on its size and distance. A larger planet reflects more light than a smaller planet. A closer planet appears brighter than a distant planet. Planet Y would be small and distant. It would reflect an incredibly tiny amount of sunlight. Even with the largest telescopes on Earth, it would be extremely faint. Possibly fainter than the background noise in our images. To make matters worse, Planet Y would be moving slowly. Objects in the outer solar system take decades or centuries to complete their orbits. From our perspective, they barely move against the background stars. This makes them easy to mistake for distant stars or galaxies. Astronomers find distant solar system objects by taking multiple images of the same region of sky over several nights or weeks. They look for objects that move between the images. Stars and galaxies are so far away, they don't appear to move. But objects in our solar system do move. By comparing images, astronomers can identify moving objects and track their orbits. This technique works well for objects in the inner Kuiper belt because they move fast enough to be noticeable over short time periods. But objects in the outer Kuiper belt move so slowly that you need observations spanning years to detect their motion reliably. And that's for objects we know exist. For a hypothetical object, like Planet Y, we don't know where to look. We have to survey huge areas of sky repeatedly over long periods. That requires enormous amounts of telescope time. Time that's in high demand from astronomers studying everything from nearby stars to distant galaxies to supernova explosions. Getting enough time on major telescopes to conduct a thorough search for Planet Y is a significant challenge. Several surveys are underway. The Vera Rubin Observatory, formerly called the Large Synoptic Survey Telescope, is a new facility in Chile that will survey the entire visible sky every few nights. It's specifically designed to find moving objects. When it begins full operations, it will dramatically increase our ability to find faint, distant objects in the outer solar system. If Planet Y exists and is bright enough, the Vera Rubin Observatory should find it within a few years. Other searches are using existing telescopes. The Subaru telescope in Hawaii has been conducting surveys of the outer solar system for years. The Canada-France-Hawaii telescope has also been used for similar surveys. Each survey images a portion of sky, looking for faint, moving objects. The data is processed by computers that automatically identify potential candidates. Then, astronomers follow up on the most promising candidates to determine their orbits and confirm they're real objects, not artifacts or background galaxies. It's painstaking work. Thousands of images, millions of potential detections. Most turn out to be noise or known objects. But occasionally, something new appears. Over the last few decades, this process has discovered hundreds of Kuiper belt objects. Each discovery helps us understand the population and distribution of objects in the outer solar system. And each discovery refines our models of how the solar system formed and evolved. But so far, Planet Y hasn't shown up. That doesn't mean it doesn't exist. It might be fainter than we expected. It might be in a part of the sky that hasn't been surveyed yet. It might be in a region of sky that's difficult to observe because it's near the plane of the Milky Way, where the background star density makes it hard to identify moving objects. There are many reasons why a real object might have escaped detection so far. Absence of evidence isn't evidence of absence, especially when we're searching for something incredibly difficult to find in the first place. But the longer we search without finding Planet Y, the more constrained its properties become. If it was very large and very close, we probably would have found it by now. So, if it exists, it's either smaller, farther, or both. Each year of searching without a detection narrows the possibilities. Let's talk about what Planet Y would actually be like. Imagine a world roughly the size of Earth, or perhaps smaller, like Mercury or Mars. A rocky planet with a solid surface. But unlike Earth, this world receives almost no sunlight. At 45 astronomical units, the distance Planet Y likely orbits, the Sun would appear as an intensely bright star, but only about 0.04% as bright as it appears from Earth. Think about that for a moment. From Earth, the Sun is so bright you can't look directly at it. It illuminates the entire sky during the day. It provides warmth, light, energy. Life on Earth depends completely on sunlight. From planet-wise distance, the sun would still be the brightest object in the sky by far. Brighter than any star. Bright enough to cast shadows. But those shadows would be faint. And the light would provide almost no warmth. The amount of energy per square meter reaching planet Y would be about 2,500 times less than what reaches Earth. That's not enough to provide meaningful warmth. The surface temperature would be determined primarily by internal heat and any residual warmth from the planet's formation. For a small, rocky planet, that internal heat would have largely dissipated over the billions of years since the solar system formed. Rocky planets generate internal heat from radioactive decay of elements like uranium, thorium, and potassium. But for a planet the size of Earth, or smaller, this heat production is relatively modest. Earth's internal heat keeps the core molten and drives plate tectonics and volcanism. But Earth also has the sun to keep its surface warm. Without the sun, Earth's surface would freeze solid within a few million years. The atmosphere would condense and fall as snow. The oceans would freeze to the bottom. The surface temperature would drop to the background temperature of space. Planet Y would be in that state, frozen solid. The surface temperature would be close to the temperature of space itself, around 40 Kelvin. That's negative 387 degrees Fahrenheit, negative 233 degrees Celsius. At this temperature, everything freezes. Water ice is harder than steel. Carbon dioxide is a solid. Nitrogen is a solid. Methane is a solid. Any atmosphere planet Y might have had when it formed would have frozen out billions of years ago. If planet Y formed in the inner solar system, it might have started with an atmosphere similar to Earth's or Mars's. But once it was scattered to the outer solar system, that atmosphere would have condensed. Nitrogen would have frozen and fallen to the surface as snow. Oxygen would have frozen. Carbon dioxide would have frozen. Water vapor would have frozen. Over millions of years, the entire atmosphere would have been deposited on the surface as layers of frost and ice. The result would be a thin, airless world covered in frozen volatiles. Not completely airless. There might be a trace atmosphere. At 40 Kelvin, some substances have non-zero vapor pressures. Neon remains gaseous even at these temperatures. Hydrogen and helium, if they were ever present, would have escaped to space long ago because they're light and the planet's gravity might not be strong enough to hold them. But heavier noble gases, like argon, might persist in trace amounts. The atmosphere, if you can call it that, would be incredibly tenuous. Millions of times thinner than Earth's atmosphere. For practical purposes, Planet Y's surface would be exposed directly to space. The landscape would be alien beyond imagination. Jagged mountains of rock and ice rising under a black sky. Craters from ancient impacts, perfectly preserved because there's no erosion, no wind to wear them down, no water to wash them away, no tectonic activity to resurface the planet. Every impact crater from the last 4 billion years would still be there. The geology would be frozen in time. The surface might be covered in a layer of frost, nitrogen, ice, methane ice, carbon dioxide ice, water ice. These ices would be mixed with rock and dust. The exact composition would depend on what volatiles were present when planet Y was ejected from the inner solar system. If it formed in the same region as Earth, it might have similar proportions of water and carbon. If it formed closer to the Sun, it might be drier. If it formed farther out, near the ice line, it might be richer in volatiles. We won't know until we find it and study it. The color of the surface is an interesting question. Fresh ice is white or light-colored. But in the outer solar system, ice doesn't stay fresh. Cosmic rays, high-energy particles from space, constantly bombard the surface. Ultraviolet light from the sun, faint as it is, also reaches the surface. These energy sources break apart simple molecules like methane, nitrogen, and carbon dioxide. The fragments recombine into more complex organic molecules called tholins. Tholins are dark, reddish-brown compounds. They're responsible for the color of Pluto's surface. They're found on many outer solar system objects. If planet Y has been in the outer solar system for billions of years, its surface is probably covered in a layer of tholins. The planet would be dark, reddish or brownish in color, reflecting only a small fraction of the already faint sunlight that reaches it. That's part of why it's so hard to find. The sun would be visible, of course. A brilliant point of light in the black sky, much brighter than any star, but small. From 45 astronomical units, the sun would appear about 0.02 degrees across. For comparison, from Earth, the sun appears about half a degree across. From planet Y, it would be 25 times smaller in angular size. Still visible as a disk if you looked at it through a telescope, but to the naked eye, it might appear almost point-like. The stars would be spectacular. With no atmosphere to scatter light, the stars would be unwavering, sharp points of light. The Milky Way would be a brilliant band across the sky, brighter than it ever appears from Earth, even in the darkest locations. Because there's no atmospheric scattering, no air glow, no light pollution, just pure starlight. You could see stars during the daytime, if there is a meaningful distinction between day and night. The day and night cycle would depend on planet Y's rotation rate. We have no idea how fast it spins. Earth rotates once every 24 hours. Mars rotates once every 24.6 hours. Venus rotates once every 243 Earth days. Mercury rotates 3 times for every 2 orbits around the Sun, a 3-to-2 spin-orbit resonance. Planet Y could have any of these rotation patterns, or something completely different. If it formed in the inner solar system, it might have started with a rotation similar to Earth or Mars. But gravitational interactions during its ejection from the inner solar system could have altered its spin. A close encounter with Jupiter or Saturn could have sped up its rotation or slowed it down. An impact from a large object during the solar system's chaotic early days could have changed its rotation axis or rate. If planet Y is tidally locked to the Sun, one side would permanently face the Sun and the other side would permanently face away. But tidal locking requires time and proximity. The closer an object is to the Sun, and the more time it spends there, the more likely tidal locking becomes. At planet Y's distance, tidal forces from the Sun are weak. The timescale for tidal locking would be trillions of years, far longer than the age of the solar system. So planet Y is almost certainly not tidally locked. It probably rotates independently of its orbit. If it rotates relatively fast, say once every 10 to 50 hours, then day and night would cycle regularly. but the difference between day and night would be minimal. During the day, the sun would provide faint illumination, dim twilight at best. During the night, the sun would be below the horizon, and the only light would be starlight. The temperature difference between day and night would be small. The sun's heat is so weak that it doesn't significantly warm the surface. The surface temperature would be determined by internal heat and the thermal inertia of the surface materials. Rock and ice don't change temperature quickly. So even if the sun provides a little extra energy during the day, the surface temperature would barely rise, a few degrees at most. And at night, the surface would barely cool. The temperature would remain nearly constant, hovering around 40 Kelvin. If planet Y rotates very slowly, like Venus, the day-night cycle would be stretched over months or years. One side would gradually warm, slightly, as it faces the sun. The other side would gradually cool slightly, as it faces away. But again, the temperature changes would be minimal. The sun is simply too faint to make a significant difference. One interesting aspect of Planet Y's environment is radiation. In the outer solar system, objects are bombarded by cosmic rays, high-energy particles from supernovas and other cosmic sources. Earth is protected from cosmic rays by its magnetic field and atmosphere. The magnetic field deflects charged particles. The atmosphere absorbs what gets through. Only a small fraction of cosmic rays reach Earth's surface. Planet Y, with no magnetic field and no atmosphere, would be fully exposed. The surface would be constantly bombarded by high-energy protons, electrons, and atomic nuclei. Over time, this radiation would alter the surface materials, breaking chemical bonds, creating new compounds, darkening the surface. This is why outer solar system objects tend to be darker than inner solar system objects. The radiation processing creates complex organic molecules that absorb light. If humans ever visited Planet Y, they would need protection from this radiation. Spacesuits would need shielding. Habitats would need to be built underground or shielded with layers of ice and rock. Surface exploration would be hazardous without proper precautions. But we're a long way from worrying about that. First, we need to find Planet Y. Then we need to study it from a distance. Only after decades of telescopic observation would it make sense to consider a mission, and even then, the journey would take decades more. So surface exploration of Planet Y, if it exists, is probably a century or more in the future. For now, it remains a world of imagination and simulation. A frozen, dark, silent world orbiting in the outermost reaches of our solar system, untouched by human eyes, unknown to human science, waiting to be discovered. If you stood on Planet Y's surface, you'd see no motion, no wind, because there's no atmosphere to move, no water flowing, because there's no liquid water, no life, because the conditions are far too extreme, just frozen stillness under the faint light of distant stars. The day and night cycle would depend on Planet Y's rotation rate. We have no idea how fast it spins. It could rotate in a few hours like Earth, creating rapid day-night cycles. Or it could be tidally locked, always keeping one face toward the sun like the moon does toward Earth. Or it could have a very slow rotation, like Venus or Mercury. Without observations, we simply don't know. If Planet Y formed in the inner solar system and was scattered outward, it might have a rotation similar to the terrestrial planets. If it's a captured rogue planet, its rotation could be anything. It might even be tumbling chaotically if it had a violent history of collisions or near misses with other planets. One interesting question is whether Planet Y could have moons. Many objects in the outer solar system have moons. Pluto has 5 known moons. Haumea has 2. Makemake has 1. Even some of the smaller Kuiper Belt objects have companions. It's possible Planet Y has moons. If it does, they would share the same frozen environment. Small worlds of rock and ice, orbiting a larger world of rock and ice, all lost in the darkness beyond Neptune. Finding moons around Planet Y would actually help us understand its origin. If the moons formed with Planet Y in the inner solar system, they might have different compositions than moons that formed in the outer solar system. Studying them could tell us where Planet Y came from. But we're getting ahead of ourselves. First, we need to find Planet Y itself. Then, we can worry about moons. Let's consider the broader implications if Planet Y exists. The discovery of a rocky planet in the outer solar system would fundamentally change our understanding of solar system formation. Current models suggest that rocky planets form close to the Sun, and giant planets form farther out. This makes sense based on the temperature gradient in the early solar system. Close to the young Sun, temperatures were high. Several thousand Kelvin in the very innermost regions. At these temperatures, only materials with high condensation temperatures could exist as solids: rock and metal, silicates like olivine and pyroxene, iron and nickel. These materials condensed from the disk of gas and dust surrounding the young Sun. They stuck together through collisions, gradually building up larger and larger bodies. First, dust grains, then pebbles, then boulders, then mile-sized planetesimals, then moon-sized planetary embryos. Finally, full-sized planets. This process, called accretion, is well understood. We've observed it happening in protoplanetary disks around other young stars. We've simulated it in computer models. We're confident this is how the terrestrial planets formed. But this process only works close to the Sun, where it's hot enough that volatiles like water, carbon dioxide, and methane remain as gases. Farther from the Sun, beyond what's called the ice line, temperatures drop below the condensation points of these volatile compounds. The ice line is typically around 2.7 to 4 astronomical units in our solar system. Beyond this distance, water ice can condense as a solid. This dramatically increases the amount of solid material available for planet formation. Suddenly, you have not just rock and metal, but also water ice, carbon dioxide ice, methane ice, and ammonia ice. In the early solar system, roughly half of the solid material was ice. This gave the outer regions much more building material. Planets could grow larger. And once they grew large enough, their gravity could capture hydrogen and helium from the surrounding gas. That's how the giant planets formed. Jupiter, Saturn, Uranus, and Neptune all started as rocky, icy cores. But they grew massive enough to hold on to thick atmospheres of hydrogen and helium. Jupiter and Saturn captured so much gas that they became primarily gaseous. Uranus and Neptune captured less gas, remaining more icy in composition. But all four formed beyond the ice line where ice was available. The inner planets, Mercury, Venus, Earth, and Mars formed inside the ice line. They're made primarily of rock and metal. They're smaller because less solid material was available. And they couldn't capture significant atmospheres of hydrogen and helium because they never grew massive enough. This basic picture has been the standard model for decades, and it works well to explain the architecture of the solar system. Small rocky planets close in. Giant planets farther out. Everything makes sense based on where materials could condense and how much material was available. Planet Y doesn't fit this picture. If it exists, it's a rocky planet in the outer solar system. A world that should have formed close to the Sun, but is now far from it. How do we explain that? There are several possibilities, and each has different implications for how planetary systems form and evolve. One idea, which I mentioned earlier, is that Planet Y formed in the inner solar system along with Mercury, Venus, Earth, and Mars, but was scattered outward by gravitational interactions with the giant planets. This scenario is actually quite plausible. Computer simulations of the early solar system show that planet formation was chaotic. Dozens or even hundreds of planetary embryos formed in the inner solar system. Most of them collided with each other or with the growing planets. These collisions built up the final planets. Earth probably grew through dozens of major collisions with Moon-sized to Mars-sized objects. The Moon itself formed from debris ejected during a giant impact between Earth and a Mars-sized body called Theia. But not all planetary embryos collided. Some had close encounters that changed their orbits without leading to collision. A close encounter with a massive planet like Jupiter could have dramatically altered a smaller planet's orbit. If a rocky planet swung close to Jupiter at the right angle and speed, Jupiter's gravity could have flung it into a much larger orbit. This is called gravitational scattering. It's a well-understood process. We see it happening in planetary systems around other stars. Hot Jupiters, massive planets orbiting very close to their stars, probably formed farther out and migrated inward. During that migration, they would have scattered other planets, some inward toward the star, some outward away from the star. In our solar system, Jupiter probably migrated. Not as dramatically as hot Jupiters in other systems, but enough to have significant effects. Early models suggested Jupiter formed farther from the Sun and moved inward. More recent models suggest Jupiter might have moved inward and then back outward in a process called the Grand Tack. During this migration, Jupiter would have scattered countless smaller objects. Many planetary embryos in the inner solar system would have been ejected. Some fell into the Sun. Some were kicked out of the solar system entirely. Some might have been thrown into distant orbits. Planet Y could be one of those scattered worlds. A planetary embryo that formed in the inner solar system but was kicked out to the edges by an encounter with Jupiter or Saturn. If this scenario is correct, Planet Y would have an interesting composition. It would be made of the same materials as the terrestrial planets. Rock rich in silicates and iron. Possibly some water if it formed beyond Earth's orbit, but inside the ice line. Studying Planet Y's composition would tell us about conditions in the early inner solar system. It would be like having a preserved sample of a world that was ejected billions of years ago. A time capsule from the solar system's youth. Another possibility is that Planet Y formed where it is. This seems less likely, but it's not impossible. In the standard model, beyond the ice line, Planets should grow large because ice is available. They should become giant planets. But maybe, in some rare cases, a rocky planet could form in the outer solar system. How might this happen? One scenario involves local concentrations of material. If there was a ring or clump of rocky material in the outer solar system, perhaps left over from some earlier process, a planet could have formed there. Maybe a large icy body broke apart, releasing its rocky core. Maybe material from the inner solar system was scattered outward early on, before the giant planets formed, and concentrated in a particular region. These scenarios are speculative. They require special circumstances. But the universe is a big place, and special circumstances do happen. Another scenario involves late-stage planet formation. Most planet formation happens in the first 10 million to 100 million years of a star's life. That's when the protoplanetary disk is still present, full of gas and dust. But some planet formation can continue later. After the gas has been blown away by stellar winds and radiation, solid objects can still collide and grow. This process is slower because there's no gas to help damp down eccentric orbits. But it can still happen. If a rocky planet formed late in the outer solar system, it could have grown from the collision and merger of many smaller icy and rocky bodies. The ice would have been lost over time through impacts and sublimation, leaving behind a rocky core. This is also speculative. We don't have strong evidence that this process happens, but it's theoretically possible. A third, more exotic possibility is that Planet Y is a captured rogue planet. A world that formed around another star, was ejected from its home system, and wandered through interstellar space until our sun's gravity captured it. Rogue planets are real. We've detected them drifting through space between the stars. They don't orbit stars, so they don't reflect starlight, but they do emit faint infrared radiation from leftover heat from their formation. Infrared surveys have found isolated planetary mass objects floating in star-forming regions. Objects too small to be stars, but not orbiting anything. These are rogue planets. How common are rogue planets? We don't know for sure. Early estimates, based on microlensing surveys, suggested there might be as many rogue planets as there are stars in the galaxy. Hundreds of billions. More recent estimates are more conservative, suggesting perhaps one rogue planet for every few stars. But even at the lower estimate, that's tens of billions of rogue planets wandering the Milky Way. How do rogue planets form? Some might form in protoplanetary disks and then get ejected by gravitational interactions. Others might form directly from collapsing gas clouds, like stars do, but without gathering enough mass to ignite fusion. Once ejected or formed, these planets wander through space. They're not bound to any star. They orbit the galaxy as a whole. Most will wander forever, never encountering another star. But occasionally, a rogue planet might pass close to a star. If the geometry is right, the star's gravity could capture the planet. The planet would settle into an orbit around the star. For capture to work, the planet needs to lose energy. Otherwise, it would just swing past the star and continue into space. There are a few ways this could happen. If the star has a protoplanetary disk when the planet passes by, friction with the disk could slow the planet down enough for capture. If the star has other planets, a gravitational interaction with one of them could change the rogue planet's trajectory, putting it into a bound orbit. If the rogue planet has its own moon or companion, a process called tidal capture might work. The tidal forces during the close pass could extract energy from the system, leaving the planet in orbit. None of these processes are common. Capture is rare, but it's not impossible. And if our solar system captured a rogue planet billions of years ago, that planet could still be orbiting out there. If Planet Y is a captured rogue planet, it would have an unusual composition. It might be made of materials that don't match anything in our solar system. Different isotope ratios, different mineral compositions. These differences would reveal its foreign origin. Studying Planet Y would be like studying a piece of another planetary system. That would be extraordinary. We could learn about planet formation around other stars without leaving our solar system. We could compare Planet Y's composition to the composition of exoplanets detected by telescopes. We could gain insights into the diversity of planets in the galaxy. So the origin of Planet Y, if it exists, is an open question. Was it scattered from the inner solar system? Did it form in place? Is it a captured rogue planet? Each possibility has different implications, and each can be tested through observations. Measuring Planet Y's orbit would tell us about its dynamical history. An orbit that's consistent with scattering from the inner solar system would support that scenario. An orbit that's highly inclined or retrograde might favor the rogue planet hypothesis. Measuring Planet Y's composition would provide more clues. A composition similar to Earth or Mars would support the scattered scenario. A composition that doesn't match solar system materials would support the rogue planet hypothesis. Finding moons around Planet Y would also be informative. Moons that formed with the planet would have similar compositions. Moons that were captured later might have different compositions. The number and characteristics of moons could constrain the planet's history. All of this, of course, requires finding Planet Y first. Until we detect it, all we have are models and speculations. But that's part of the excitement of science. We formulate hypotheses. We make predictions. We design observations to test those predictions. And eventually, we get answers. Those answers might confirm our ideas, or they might surprise us completely. Either way, we learn, and our understanding of the universe deepens. Planet Y would be an exception, an outlier that doesn't fit the pattern. That's actually exciting for scientists, because outliers often teach us the most. When something doesn't fit your model, it means your model is incomplete. It means there's something you don't understand. Figuring out why Planet Y is where it is would require refining our models of how planets form and migrate. It would give us new insights into the early solar system, when planets were still moving around and interacting gravitationally. It might tell us that scattering of terrestrial planets was more common than we thought. Maybe other rocky planets were ejected from the solar system entirely, flung into interstellar space billions of years ago. Maybe we got lucky, and one of them ended up in a distant but stable orbit. Or maybe Planet Y tells us something completely different. Maybe it formed where it is through some process we haven't considered yet. Science advances by discovering things that don't fit our expectations. Planet Y would be one of those discoveries. The existence of Planet Y would also affect our census of the solar system. For most of human history, we thought there were 6 planets: Mercury, Venus, Earth, Mars, Jupiter, and Saturn. Those are the planets visible to the naked eye. Then, in 1781, William Herschel discovered Uranus using a telescope. In 1846, Neptune was discovered based on mathematical predictions. In 1930, Pluto was discovered. For 76 years, Pluto was considered the ninth planet. Then, in 2006, the International Astronomical Union redefined what a planet is. Under the new definition, Pluto didn't qualify because it hasn't cleared its orbit of other debris. Pluto was reclassified as a dwarf planet. The solar system went from 9 planets back to 8. This was controversial. Many people, especially in the United States where Pluto was discovered, felt attached to Pluto as a planet. The debate continues to this day. Some scientists argue the definition should be changed. Others defend it. But here's the thing. If Planet Y exists and is large enough, it would almost certainly qualify as a planet under the current definition. A world the size of Mercury or larger would have enough gravity to pull itself into a round shape. That satisfies one criterion. It would orbit the Sun. That satisfies another criterion. The question would be whether it has cleared its orbit. Given its distance and isolation, it probably has. There aren't many objects in the outer Kuiper belt compared to the inner regions. Planet Y would be the dominant gravitational force in its region, so it would qualify as the 9th planet. The solar system would go from 8 planets back to 9. That would be a big deal. Not just scientifically, but culturally. Textbooks would need to be rewritten. Planetarium shows would need to be updated. Children would learn about 9 planets instead of 8. The narrative of our solar system would change. But more importantly, it would remind us how much we still don't know about our own cosmic backyard. We've been studying the solar system for centuries. We've sent spacecraft to every major planet. We've mapped their surfaces, measured their atmospheres, studied their moons. And yet, there might be an entire planet we haven't found yet, hiding in the darkness, invisible to our telescopes so far, but there nonetheless. That's humbling. It tells us that even in our own neighborhood, even in a system we've been studying for generations, there are still mysteries, still unknowns, still discoveries waiting to be made. It's worth noting that Planet Y is just one of several hypothetical objects that might exist in the outer solar system. I mentioned Planet 9 earlier. That's the most famous one. But there are others. Some astronomers have proposed the existence of an Earth-mass planet in the inner Oort cloud. Others have suggested there might be several smaller planets scattered throughout the outer solar system. Each hypothesis is based on different observations and different anomalies in the orbits of known objects. The outer solar system is so vast and so poorly explored that multiple undiscovered planets could be hiding out there. We simply don't know yet. Every few years, new surveys find new objects. Each new object adds a data point. Each data point refines our models. Gradually, we're building a complete picture of what's out there. But it's a slow process. The distances are enormous. The objects are faint. The surveys take years or decades. We need patience. Science doesn't happen overnight. It happens through careful observation, rigorous analysis, and persistent searching. The astronomers looking for Planet Y are conducting surveys that will continue for years. They're taking images, processing data, following up on candidates, ruling out false positives. Each step brings us closer to an answer. Either we'll find planet Y, or we'll constrain its properties so tightly that we can say with confidence it doesn't exist. Both outcomes are valuable. Finding it would be exciting. Ruling it out would also be important because it would tell us the warp in the Kuiper belt has a different explanation. Maybe one we haven't thought of yet. That would be its own discovery, pointing us toward new physics or new understanding of orbital dynamics. Let me take a step back and talk about why this matters. Why should you care about a hypothetical planet billions of miles away in the frozen darkness? There are several reasons. First, understanding our solar system helps us understand planets in general. We've discovered thousands of planets around other stars. We call them exoplanets. These planets come in all sizes and orbit at all distances from their stars. Many don't fit the patterns we see in our own solar system. There are hot Jupiters, gas giants, orbiting closer to their stars than Mercury orbits our Sun. There are super-Earths, rocky planets larger than Earth but smaller than Neptune. There are planets orbiting binary stars, planets in highly eccentric orbits. The diversity is staggering. By understanding our own solar system in detail, including oddities like Planet Y if it exists, we gain insights into how planetary systems form and evolve. We learn what's typical and what's unusual. We learn which processes are universal and which are specific to certain conditions. This knowledge helps us interpret observations of exoplanets. It helps us predict where to find habitable worlds. It helps us understand our place in the universe. Second, searching for Planet Y pushes the boundaries of observational astronomy. The techniques being developed to find faint, distant objects in our own solar system are the same techniques used to study distant galaxies, asteroids that might threaten Earth, and other phenomena. Improving our ability to detect faint moving objects has applications far beyond finding Planet Y. It helps us protect Earth from asteroid impacts. It helps us track potentially hazardous space debris. It helps us discover comets before they become visible to the naked eye. The search for Planet Y is driving technological and methodological improvements that benefit astronomy as a whole. Third, there's the simple wonder of discovery. Humans are explorers. We're curious by nature. We want to know what's out there. The possibility that an entire planet exists in our solar system, undiscovered, is thrilling. It reminds us that the universe still has secrets, that there are still frontiers to explore, that even in an age of smartphones and the internet, there are profound mysteries waiting to be solved. The discovery of Planet Y, if it happens, would be one of the great astronomical discoveries of the 21st century. It would rank alongside the discovery of exoplanets, the detection of gravitational waves, and the imaging of black hole shadows. A milestone in our understanding of the cosmos. And you're alive to witness it. That's special. It's easy to take these discoveries for granted. We live in an era of constant scientific advancement. New discoveries are announced regularly, but each one represents years or decades of work by dedicated scientists. Each one expands the boundaries of human knowledge. Each one changes how we see ourselves and our place in the universe. Whether Planet Y exists or not, the search for it is valuable. The search is teaching us about the outer solar system. It's refining our models. It's pushing technology forward. It's engaging the public's imagination. And someday, maybe soon, maybe years from now, someone will analyze a set of telescope images and notice a faint point of light that moved between frames. They'll follow up with more observations. They'll calculate an orbit, and they'll realize they've found it. Planet Y, the mysterious world hiding beyond Neptune. When that happens, it will be a moment of triumph, the culmination of years of effort, a new chapter in the story of our solar system. Or maybe the search will continue, and eventually, the constraints will become so tight that we'll conclude Planet Y doesn't exist. The warp in the Kuiper belt will turn out to have a different explanation. Maybe a swarm of smaller objects. Maybe an effect we hadn't considered. That would also be valuable. It would close one chapter and open another. Science is about asking questions and seeking answers. Sometimes the answer is yes. Sometimes it's no. Both are progress. What would it be like to visit Planet Y? Imagine a spacecraft making the journey. This isn't pure fantasy. We've sent spacecraft to every major planet in the solar system. We've even sent probes beyond Pluto into interstellar space. A mission to Planet Y would be technically possible, though extraordinarily challenging. Let me walk you through what such a mission might look like. First, the spacecraft would need to be designed for the extreme conditions of the outer solar system. At Planet Y's distance, sunlight is too faint for solar panels to provide useful power. The spacecraft would need a different energy source. A radioisotope thermoelectric generator, or RTG. This is a nuclear battery that converts heat from radioactive decay into electricity. The Voyager spacecraft used RTGs. The New Horizons probe that flew past Pluto used an RTG. The Curiosity and Perseverance, rovers on Mars, use RTGs. They're reliable, long-lasting, and work regardless of sunlight. An RTG for a Planet Y mission would probably use plutonium-238 as the radioactive fuel. This isotope has a half-life of about 88 years. It produces heat through radioactive decay, and thermocouples convert that heat to electricity. The power output is modest, maybe a few hundred watts. But that's enough to run the spacecraft's instruments and communication systems. Second, the spacecraft would need propulsion. Getting to Planet Y would require a lot of delta V. Delta V is the change in velocity needed for a space maneuver. To reach the outer solar system, you need to accelerate to high speeds. The New Horizons mission reached Pluto in about 9.5 years. It was launched on one of the most powerful rockets available, the Atlas V. It received a gravity assist from Jupiter, using Jupiter's gravity to increase its speed. At its fastest, New Horizons was traveling about 10 miles per second relative to the Sun. Planet Y is farther than Pluto. A mission to Planet Y would probably take 15 to 25 years, depending on the trajectory and whether gravity assists from the giant planets are used. That's a long time. The spacecraft would need to be built to last. All systems would need to be redundant. Software would need to be robust. Components would need to survive decades in the harsh environment of space. Cosmic radiation would gradually degrade electronics. The RTG's power output would slowly decline as the plutonium decays. Engineers would need to plan for all of this. Third, the spacecraft would need scientific instruments, cameras to image Planet Y as it approaches. spectrometers to analyze the composition of the surface, magnetometers to measure any magnetic field, particle detectors to study the radiation environment, radio science experiments to measure the planet's mass and gravitational field. Each instrument would need to be carefully chosen to maximize the science return within the constraints of mass, power, and data rate. Fourth, communication would be a challenge. Radio signals travel at the speed of light. From 45 astronomical units, a radio signal would take about 6 hours to reach Earth. That's a one-way, light time. If mission controllers send a command to the spacecraft, the command takes 6 hours to arrive. If the spacecraft sends back an acknowledgement, that takes another 6 hours. 12 hours, round-trip communication time. This makes real-time control impossible. The spacecraft would need a high degree of autonomy. It would need to make decisions on its own. If it detects an interesting feature on planet Y and wants to take a closer look, it can't wait 12 hours for instructions from Earth. It needs to decide and act immediately. This requires sophisticated onboard software, artificial intelligence, and machine learning algorithms that can recognize interesting targets and adjust the spacecraft's observations accordingly. The data rate would also be limited. At that distance, the spacecraft's radio signals would be incredibly faint by the time they reach Earth. Even with large receiving antennas on Earth, the data rate might be only a few kilobits per second. Compare that to a typical home internet connection, which might be tens or hundreds of megabits per second. The spacecraft would transmit data thousands of times slower. High-resolution images would take hours or days to transmit. Mission planners would need to carefully prioritize what data to send back first. Fifth, the mission would need to decide on the trajectory. A flyby mission would be faster and simpler. The spacecraft would approach planet Y, take observations during a brief encounter, and then continue past into the outer solar system. New Horizons did this with Pluto. The encounter lasted only a few hours. The spacecraft collected as much data as possible during that window. Then it spent months transmitting the data back to Earth. A flyby mission to planet Y would work similarly. The advantage is that it doesn't require slowing down. The spacecraft can travel at high speed the entire way, reducing travel time. The disadvantage is that the encounter is brief. Once the spacecraft passes planet Y, it's gone forever. There's no second chance to observe something you missed. An alternative would be an orbiter mission. The spacecraft would slow down when it reaches planet Y and enter orbit around the planet. This allows extended observation. The spacecraft could map the entire surface over time. It could study seasonal changes if planet Y has seasons. It could search for moons. It could make detailed measurements of the planet's gravity field, rotation, and composition. The disadvantage is that entering orbit requires a lot of fuel. You have to slow down from interplanetary speeds to orbital speeds. That's a huge delta-V requirement. It would probably require a much larger and more expensive spacecraft. And the mission would take longer because the spacecraft couldn't travel as fast if it needs to carry all that fuel. A compromise might be a mission that does multiple flybys. The spacecraft would fly past planet Y, then loop around and come back for another pass. This could be done using gravity assists from Neptune or other bodies. Each flyby would provide another opportunity to observe the planet. This approach has been used successfully for missions to Jupiter's moons and Saturn's moons. The Cassini spacecraft made dozens of flybys of Saturn's largest moon, Titan, gradually building up a complete picture. A similar approach could work for Planet Y. Sixth, the mission would need funding. Space missions are expensive. The New Horizons mission cost about $700 million. A mission to Planet Y would probably cost at least that much, possibly more. NASA's budget for planetary science is limited. There are many competing priorities. Missions to Mars. Missions to the icy moons of Jupiter and Saturn. Missions to Venus. Missions to asteroids. Each mission competes for funding. To get approval, a Planet Y mission would need to make a compelling scientific case. It would need to show that the science return justifies the cost, and it would need to compete against other proposals. This is part of why we haven't sent a mission to search for Planet Y yet. We don't even know if it exists. It would be hard to justify spending hundreds of millions of dollars on a mission to a planet that might not be there. First, we need to find Planet Y with telescopes. Once we know it exists, once we've measured its orbit and basic properties, then a mission becomes feasible. Seventh, the timeline would be long. From proposal to launch typically takes a decade or more for a major planetary mission. Scientists propose the mission. It undergoes peer review. If approved, engineers design the spacecraft. Instruments are built and tested. The spacecraft is assembled. Everything is tested extensively. Only then is it ready for launch. Then comes the 20-year flight to Planet Y. Then months or years of observations. Then months or years of transmitting data back to Earth. Then years of analyzing the data and publishing results. From start to finish, a mission to Planet Y could easily take 40 or 50 years. Scientists who work on the proposal might retire before the mission reaches its target. Graduate students who work on the instruments might be senior professors by the time they analyze the return data. This long timeline is both a challenge and an opportunity. It's a challenge because it requires sustained commitment across generations of scientists and engineers. Funding agencies need to commit to supporting the mission for decades. Political support needs to remain stable despite changes in administration. Technical knowledge needs to be passed from one generation to the next. But it's also an opportunity. A mission to Planet Y would inspire young people to pursue careers in science and engineering. It would provide employment for thousands of people over decades. It would produce scientific discoveries that advance our understanding of the solar system. And it would demonstrate humanity's capability for long-term planning and execution. These are the kinds of projects that define a civilization. Not what we accomplish in a year or even a decade, but what we're willing to commit to over generations. Eighth, the science return would be extraordinary. Direct observations of Planet Y would tell us things we can never learn from Earth-based telescopes alone. High-resolution images of the surface would reveal its geology. Crater counts would tell us the age of the surface. Spectroscopy would identify the minerals and ices present. Measurements of the planet's shape and rotation would constrain its internal structure. Does it have a dense metallic core like Earth? Or is it more uniform in composition? Measurements of the magnetic field would tell us about the interior. A magnetic field requires a liquid metallic core with convective motion. Earth has a magnetic field generated by its liquid iron core. Mars has no global magnetic field because its core has solidified. Does planet Y have a magnetic field? That would tell us whether its core is still partially molten, which would tell us how much heat it retains from formation. Searching for moons would be a priority. Moons can tell us a lot about a planet's history. If planet Y has moons, how did they form? Did they form with the planet? Were they captured later? Are they fragments from a collision? Each scenario has different implications. The spacecraft could also study planet Y's interaction with the solar wind. The solar wind is a stream of charged particles flowing out from the sun. At planet Y's distance, the solar wind is weak but still present. How does it interact with the planet's surface and any tenuous atmosphere? Does it erode the surface? Does it create any phenomena similar to auroras on Earth? These questions can only be answered by in situ measurements, by being there, by observing directly. That's the power of planetary exploration. We can learn some things from a distance, but to really understand a world, we need to visit it. We need to see it up close. We need to measure it directly. That's why space exploration matters. It's not just about pretty pictures, though those are wonderful. It's about understanding, about learning how planets work, about uncovering the history of our solar system, about answering fundamental questions about our cosmic neighborhood. A mission to planet Y would be a milestone. It would expand the reach of human exploration to the farthest regions of the solar system. It would demonstrate our technical capability and our commitment to discovery. And it would bring back data that would be studied for decades, perhaps centuries. Long after the mission ends, the data would continue to yield insights. New generations of scientists would analyze it with new tools and new perspectives. That's the legacy of a great space mission. Not just the initial discoveries, but the ongoing value of the data for future generations. Leaving Earth, passing the Moon in a day, passing Mars in a few months, crossing the asteroid belt, flying past Jupiter's massive bulk, passing Saturn's rings, speeding by Uranus and Neptune, entering the Kuiper belt, and continuing outward into the darkness. The sun would shrink behind the spacecraft, slowly diminishing from a blazing disk to a bright star. The temperature would drop. Instruments designed to measure sunlight would register less and less energy. Solar panels would become useless. The spacecraft would need a different power source, probably a nuclear battery like the ones used on the Voyager and New Horizons missions. After years of travel, the spacecraft would finally approach planet Y. First, it would appear as a faint point of light. Slowly, over days or weeks, details would emerge. Is it grey like Mercury, reddish like Mars, white with frost like Pluto? We wouldn't know until we saw it. As the spacecraft draws closer, it would begin mapping the surface. Craters from ancient impacts, maybe mountains, maybe valleys. The geology would tell us about the planet's history. If the surface is heavily cratered, it means the surface is old and hasn't been resurfaced by volcanic activity or other processes. If there are smooth areas, it means something renewed the surface more recently. The spacecraft could measure the planet's mass and density. That would tell us what it's made of. Is it rocky, like Earth? Does it have a metallic core? Is it less dense, with significant ice content? These measurements would constrain its origin. The spacecraft could search for moons, study the planet's rotation, measure any magnetic field, analyze the composition of surface materials using spectrometers. Each measurement would be a piece of the puzzle. Each piece would help us understand where planet Y came from and how it got to where it is. But such a mission is far in the future. First, we need to find planet Y. Then we need to study it from Earth using telescopes. Only after we've learned as much as we can from a distance would it make sense to send a spacecraft. And even then, the journey would take decades. New Horizons, the fastest spacecraft to leave Earth, took 9.5 years to reach Pluto. Planet Y is farther. A mission would take even longer, maybe 15 or 20 years. That's a long time to wait for data, but the payoff would be worth it. Direct observations of a new planet, a world no human has ever seen before. Images transmitted across billions of miles of space, arriving on Earth to be analyzed and marveled at. That's the dream of planetary exploration. And it starts with finding the planet in the first place. I want to talk about how the search for planets in our solar system has evolved over time. Because it's a fascinating story. For most of human history, we only knew about the planets visible to the naked eye: Mercury, Venus, Mars, Jupiter, and Saturn. Ancient astronomers tracked their motions across the sky. They noticed that these objects moved against the background stars. That's why they were called planets, from the Greek word for wanderer. But they had no idea what these objects were. Some thought they were lights on a celestial sphere. Others thought they were closer than the stars, but still fundamentally different from Earth. It wasn't until the telescope was invented in the early 1600s that we could study planets in detail. Galileo turned his telescope toward Jupiter and saw moons orbiting it. That was profound. It showed that not everything orbited Earth. It challenged the geocentric model of the universe. Over the next few centuries, telescopes improved. Astronomers mapped the surfaces of Mars and the Moon. They discovered Saturn's rings. They measured the sizes of planets. They calculated their orbits with increasing precision. And in 1781, William Herschel was conducting a survey of stars when he noticed an object that appeared as a disk rather than a point of light. At first, he thought it was a comet, but after weeks of observation, it became clear the object was orbiting beyond Saturn. It was a new planet, the first planet discovered in recorded history. Herschel wanted to name it, after King George III. Fortunately, that didn't stick. It was eventually named Uranus, after the Greek deity of the sky. The discovery of Uranus showed that there were planets beyond Saturn. It expanded the known solar system, but it also created a mystery. Uranus's orbit wasn't quite right. It didn't follow the path predicted by Newton's laws of gravity when accounting for the gravitational influence of the Sun and the known planets. There were small discrepancies, deviations from the expected orbit. Astronomers wondered why. Was Newton's law of gravity wrong at large distances? Or was there another explanation? In the 1840s, two mathematicians independently worked on the problem: John Couch Adams in England and Urbain Le Verrier in France. They both hypothesized that the deviations in Uranus's orbit were caused by the gravity of an unknown planet even farther out. They calculated where this planet should be based on the observed deviations. Le Verrier sent his predictions to astronomers in Germany. On September 23, 1846, Johann Gottfried Galle pointed his telescope at the predicted location. And there it was, Neptune. A planet discovered not by accident, but by mathematical prediction. It was a triumph for Newton's laws. They weren't wrong. There was just another planet whose gravity hadn't been accounted for. This discovery had a profound impact. It showed that mathematics and physics could predict the existence of things we hadn't yet seen. It validated the scientific method, and it suggested there might be even more planets out there. In the late 1800s, astronomers noticed that Neptune's gravity didn't fully account for all the deviations in Uranus's orbit. There were still small discrepancies. So the search began for yet another planet, Planet X. Percival Lowell, a wealthy American astronomer, founded an observatory in Arizona and dedicated years to searching for Planet X. He never found it. After his death, the search continued. In 1930, Clyde Tombaugh, a young astronomer working at Lowell Observatory, discovered a faint moving object, Pluto. For 76 years, Pluto was considered the ninth planet. But over time, it became clear Pluto was different. It was much smaller than the other planets. Its orbit was highly eccentric and inclined. And starting in the 1990s, astronomers began discovering more objects beyond Neptune. Objects in the Kuiper Belt. Some were nearly as large as Pluto. One, called Eris, was actually more massive than Pluto. This created a dilemma. If Pluto is a planet, should Eris be a planet too? Should all the large Kuiper Belt objects be planets? Would we end up with dozens or hundreds of planets? In 2006, the International Astronomical Union created a formal definition of a planet. To be a planet, an object must orbit the Sun, be massive enough to pull itself into a round shape, and have cleared its orbit of other debris. Pluto failed the third criterion. Its orbit is filled with other Kuiper Belt objects. So Pluto was reclassified as a dwarf planet. This decision was controversial and remains so. But it reflects the reality that the solar system is more complex than we thought. There aren't 8 neat planets, and then nothing. There's a whole population of smaller objects. Dwarf planets, Kuiper Belt objects, scattered disk objects, each with its own story. And now we're searching for planets again. Planet 9, Planet Y, maybe others. The search continues. Each generation of astronomers pushes farther into the unknown. Each generation discovers things the previous generation couldn't imagine, and the process continues. It's a reminder that science is never finished. There's always more to discover, always new questions to ask, always new frontiers to explore. Let's talk about what happens next in the search for Planet Y. Several things need to happen. First, more observations. Astronomers need to continue surveying the sky, looking for faint moving objects. The Vera Rubin Observatory will be a game changer when it comes online. Its large mirror and wide field of view will allow it to survey the entire visible sky every few nights. It's specifically designed to find moving objects, asteroids, comets, Kuiper Belt objects, and potentially Planet Y. If Planet Y is bright enough to be detected by the Vera Rubin Observatory, it will likely be found within the first few years of operations. Second, better models. As we discover more Kuiper Belt objects and measure their orbits more precisely, we can refine the models that predict where Planet Y should be. Maybe the warp in the Kuiper Belt will become more pronounced. Maybe it will fade away. Either way, more data will constrain the possibilities. Third, Alternative explanations need to be tested. Maybe the warp isn't caused by a planet. Maybe it's caused by something else. A swarm of smaller objects. A temporary perturbation from a passing star billions of years ago. Something we haven't thought of yet. Scientists need to explore all possibilities, not just the planet hypothesis. That's how science works. You don't just accept the first explanation that fits. You test it rigorously. You look for alternative explanations. You design observations that can distinguish between the possibilities. Only after you've eliminated the alternatives do you accept the remaining explanation. And even then, you remain open to new data that might change your mind. Fourth, if Planet Y is found, we need follow-up observations. Discovering a faint moving object is just the first step. You need to observe it over months or years to determine its orbit precisely. You need to measure its brightness at different wavelengths to determine its size and composition. You need to search for moons. You need to look for any unusual features. All of this takes time and telescope resources. But it's necessary to turn a detection into a discovery, to go from seeing something move to understanding what it is. I want to address a question you might be thinking. Why haven't we found Planet Y already? We've been exploring the solar system for decades. We've sent spacecraft to every major planet. We've discovered thousands of smaller objects. Why would a planet remain hidden? The answer is distance and faintness. The outer solar system is vast. The amount of sky that needs to be surveyed is enormous. And Planet Y, if it exists, reflects very little light. Even with modern telescopes, it would be at the limit of detectability. Consider this analogy. Imagine you're in a dark stadium at night. You have a flashlight. You're looking for a small charcoal briquette somewhere on the far side of the stadium. The briquette is sitting on the ground. It's not moving. It's not glowing. It's just there. You shine your flashlight around, trying to find it. But the beam of your flashlight only illuminates a small area at a time. You have to sweep systematically. And even when your light passes over the briquette, it's so dark that it barely reflects any light back to you. You might miss it. You might think it's just a shadow or a spot on the ground. That's what searching for Planet Y is like. Except the stadium is the size of the entire sky. And your flashlight is a telescope that can only look at a tiny patch of sky at a time. And you have to not just find the object, you have to notice that it moved between observations, because that's the only way to distinguish it from background stars. It's an incredibly difficult task. The fact that we've found as many distant objects as we have is a testament to the skill and dedication of astronomers. But there's still a lot of sky we haven't searched thoroughly. Still, a lot of dark corners where something could be hiding. Planet Y could be in one of those corners. Or it could be fainter than we expected. Or it could have an unusual orbit that takes it into regions of sky we haven't surveyed yet. There are many reasons why it might have escaped detection. Patience is required. The search will continue. And eventually, we'll have an answer. Let's zoom out and think about the big picture. Our solar system formed about 4.5 billion years ago from a cloud of gas and dust. The cloud collapsed under its own gravity. The center formed the sun. The surrounding disk formed the planets, moons, asteroids, and comets. This process wasn't smooth. It was chaotic. Objects collided. Planets migrated. Some objects were ejected. Others were captured. The solar system we see today is the result of billions of years of evolution. it's not the original configuration. It's the survivors. The objects that found stable orbits and avoided collisions. Planet Y, if it exists, is a relic of that chaotic past. A world that survived but ended up in an unusual place. By finding it and studying it, we're reading the history of our solar system. We're learning about processes that happened billions of years ago, events that shaped the system we live in. That's the power of planetary science. Every planet, every moon, every asteroid has a story. By studying them, we piece together the larger narrative. The story of how our cosmic neighborhood came to be, and ultimately, the story of how we came to be. Because without the processes that formed the solar system, Earth wouldn't exist. Without Earth, life wouldn't exist. Without life, you wouldn't be here reading this. It's all connected. The search for a distant frozen planet billions of miles away connects to the deepest questions about our existence. Where did we come from? How did we get here? What is our place in the universe? These are questions humans have been asking for thousands of years. Science gives us the tools to answer them. Not with mythology or speculation, but with observations and evidence. The search for Planet Y is part of that larger quest. A small piece of a much bigger puzzle, but every piece matters. Every discovery adds to our understanding. And someday, maybe, we'll have the complete picture. Or at least a more complete picture than we have now. Because the universe is vast and complex. We'll never know everything, but we can keep learning, keep discovering, keep pushing the boundaries of knowledge. That's what makes us human. Our curiosity, our drive to understand, our refusal to accept ignorance when knowledge is possible. Planet Y might be out there, orbiting in the darkness, waiting to be found. Or it might not exist. The warp in the Kuiper Belt might have a different explanation. Either way, the search is worthwhile. The search teaches us about the solar system, about how planets form and migrate, about the limits of our observational capabilities, about how to ask questions and seek answers. That's the essence of science. Not knowing all the answers, but having the tools to search for them. One final thought. Imagine the moment when Planet Y is discovered. Imagine the astronomer who notices the faint moving object in their data, who runs the calculations and realizes what they've found, who announces the discovery to the world. That will be a historic moment, a moment of pure discovery, something that happens rarely in science. Most scientific work is incremental. Small advances building on previous work, testing hypotheses, refining measurements, gradually improving our understanding. This work is essential. It's the foundation of science. But every so often, there's a breakthrough, a discovery that changes everything. A moment when something completely new enters our understanding. The discovery of Neptune was one of those moments. It validated the power of mathematical prediction. It showed that the laws of physics could tell us things we hadn't yet observed. It expanded the known solar system. The discovery of Pluto was one of those moments. For 76 years, Pluto was considered the ninth planet. Its discovery showed that there were worlds beyond Neptune, waiting to be found. The discovery of the first Kuiper Belt object beyond Pluto was one of those moments. It revealed that Pluto wasn't alone. It showed that the outer solar system contained a whole population of icy bodies. The discovery of the first exoplanet orbiting a sun-like star was one of those moments. It proved that other stars have planets. It opened up the study of planets beyond our solar system. If Planet Y is found, it will be one of those moments. And you'll remember where you were when you heard the news. You'll remember the excitement, the wonder, the sense that the universe still has secrets, that we're still explorers on a journey of discovery. That's something to look forward to, whether it happens next year or 10 years from now or never. The possibility itself is exciting. The idea that our solar system might have more to reveal, that we're not done exploring our own cosmic backyard, that there are still worlds to discover. But beyond the excitement, beyond the headlines, there's something deeper. The search for Planet Y represents something fundamental about human nature, our curiosity, our refusal to accept ignorance when knowledge is possible, our drive to understand the universe we live in. Throughout history, humans have looked up at the sky and wondered. Ancient peoples created myths and stories to explain what they saw. The sun was a god driving a chariot across the sky. The stars were heroes or animals placed in the heavens. The planets were wandering lights with mysterious powers. These stories gave meaning to the cosmos. They helped people make sense of their world. But they weren't based on observation and evidence. They were based on imagination and tradition. Over time, we developed a better way to understand the universe. Science, the method of careful observation, rigorous testing, and evidence-based reasoning. Science doesn't rely on authority or tradition. It relies on what we can measure and verify. It's self-correcting. When new evidence contradicts an old idea, science updates. The old idea is discarded or modified. Knowledge advances. This process has revealed truths about the universe that no ancient storyteller could have imagined. The Earth orbits the Sun, not the other way around. The stars are distant suns, not lights on a celestial sphere. The universe is billions of years old and unimaginably vast. Galaxies are scattered through space like islands in an ocean. The laws of physics are the same everywhere, from the smallest particle to the largest galaxy cluster. We figured all of this out through observation and reasoning, by building telescopes and looking carefully at the sky, by measuring positions and motions and brightnesses, by developing mathematical models and testing them against reality, by being willing to challenge our assumptions and follow the evidence wherever it leads. The search for Planet Y is part of this grand tradition. We noticed something unexpected, a warp in the Kuiper belt that shouldn't be there. We asked why. We developed hypotheses. We ran simulations. We made predictions. Now we're testing those predictions through systematic observation. This is science at its best. Curiosity driving investigation. Observation leading to questions. Questions leading to hypotheses. Hypotheses leading to predictions. Predictions leading to tests. And eventually, answers. Whether Planet Y exists or not, the search is worthwhile. If we find it, we learn something new about our solar system. We discover a world we didn't know existed. We expand human knowledge. If we don't find it, we still learn something. We constrain what's possible. We rule out certain scenarios. We're forced to find alternative explanations for the observed warp. Either way, we advance. That's the beauty of the scientific method. It's not about being right. It's about getting closer to the truth, one observation at a time. About building knowledge systematically. About being willing to admit when we're wrong and change our minds based on new evidence. About following the data wherever it leads, even if it contradicts our expectations or preferences. This approach has served us remarkably well. In just a few centuries of modern science, we've learned more about the universe than all of previous human history combined. We've figured out how stars work, how galaxies form, how the universe began. We've discovered planets around other stars, black holes in distant galaxies, gravitational waves rippling through space-time. We've measured the age of the universe, the size of atoms, the speed of light, all through careful observation and rigorous thinking, all through the scientific method. The search for Planet Y also reminds us of our place in the universe. We live in a solar system that's larger and more complex than we often realize. 8 major planets, hundreds of moons, thousands of asteroids and comets, countless smaller objects, and possibly more planets waiting to be discovered. And yet, there might still be an entire planet we haven't found. A world orbiting billions of miles from the Sun, invisible to our telescopes so far, but there nonetheless. That's humbling. It reminds us that even in our own neighborhood, even in a system we've been studying intensively for generations, there are still mysteries, still unknowns, still discoveries waiting to be made. It also reminds us of the vastness of space. The distances involved are staggering. 45 astronomical units is more than 4 billion miles. Light takes 6 hours to travel that far. A spacecraft would take 20 years or more. That's how far away Planet Y might be. And that's still within our solar system, still in our cosmic backyard. Beyond the solar system, the distances become truly incomprehensible. The nearest star is over 4 light-years away. The nearest galaxy is 2.5 million light-years away. The observable universe extends for over 90 billion light-years. Compared to these cosmic scales, our solar system is tiny, a speck in an ocean. And yet, it's our speck. It's where we live. It's the only part of the universe we can realistically explore in detail with current technology. So, it matters what we find here. It matters that we map our solar system completely, that we understand how it formed and evolved, that we identify all the major worlds and characterize their properties. This knowledge is valuable for its own sake. Understanding is its own reward. But it's also valuable practically. The more we know about our solar system, the better we can predict and prepare for hazards. Asteroids that might threaten Earth, comets on collision courses, solar flares that could damage satellites and power grids. Understanding the dynamics of the solar system helps us protect ourselves. It also helps us plan for the future. If humanity expands beyond Earth, we'll need detailed knowledge of the resources available in space. Water ice on moons and asteroids, metals in asteroid cores, energy from the sun, building materials from regolith. All of these resources are out there, waiting to be used. But first, we need to find them and characterize them. The search for Planet Y is part of this larger effort to understand and map our solar system completely. It's about knowing what's out there, about eliminating the unknown, about building a complete inventory of our cosmic neighborhood. And on a personal level, the search for Planet Y speaks to something deep in the human spirit, the desire to explore, to venture into the unknown, to discover what lies beyond the horizon. This desire has driven human civilization for millennia. It led our ancestors to cross oceans, to climb mountains, to explore every continent on Earth. In the modern era, it's led us to explore space, to send humans to the moon, to send robotic probes to every planet, to peer deeper into the universe with ever more powerful telescopes. The search for Planet Y is the latest chapter in this story. A story of exploration and discovery. A story of pushing boundaries and expanding horizons. A story that's fundamentally human, because this is what we do. We explore, we discover, we learn, we push forward into the unknown, driven by curiosity and wonder. And we're never satisfied. Every answer leads to new questions. Every discovery reveals new mysteries. Every horizon we reach shows us more horizons beyond. That's what makes the search for Planet Y so compelling. It's not just about finding a planet. It's about what that planet represents, the ongoing quest for knowledge, the refusal to accept that we've learned everything there is to know, the willingness to keep searching, keep observing, keep questioning, even when the object of our search is faint and distant and difficult to find, even when the search takes years or decades, even when success is uncertain, we search anyway, because that's who we are. And because the alternative, accepting ignorance, is unthinkable. That's the beauty of science. It's never finished. There's always more to learn, always new questions, always new mysteries. Planet Y is one of those mysteries. A world that might be hiding in the darkness beyond Neptune. A world we've never seen but might exist. A world that could change our understanding of the solar system. The search continues. Telescopes scan the sky. Computers process data. Astronomers analyze results. And somewhere out there, maybe, Planet Y orbits silently, waiting. Until next time, keep looking up, keep questioning, keep wondering about the mysteries that surround us. The universe is vast and full of secrets, but we're figuring them out, one discovery at a time. Thank you for joining me on this journey to the edge of the solar system. If you found this exploration fascinating, a like or subscribe would really help the channel grow. And remember, the next time you look up at the night sky, somewhere beyond the planets you can see, beyond Neptune's orbit, there might be another world, a mysterious planet hiding in the darkness. We just haven't found it yet. Good night, and keep exploring.